Hello everyone. Today I'm going to be presenting my research for Capstone in this presentation, and we're going to be taking a look at stock embeddings for multi-asset price prediction. This is a solo project, and I've been working under the mentorship of Dr. Sam Ogden here at California State University, Monterey Bay. And today I'm going to walk you through how I applied machine learning techniques from natural language processing to financial markets and what we discovered along the way. So let me start with the core research question. Can stock embeddings reveal market structure and improve sequential prediction models? Traditional financial models treat stock independently. They look at Apple's performance, Microsoft's performance, and Google's performance as separate entities, nothing that they have in common. But in natural language processing, we have something called the word-to-vec, and that captures the semantic relationships in NLP quite nicely. It learns that king relates to queen in meaningful ways. So I wondered, can we apply the same approach to financial markets? And can Apple relate to Microsoft in ways that improve our prediction? So what are stock embeddings? To learn what stock embeddings are, we're going to take a look at that word-to-vec example we spoke about earlier. In natural language processing, word-to-vec takes words like queen, king, man, and woman and converts them into numerical vectors. These array of numbers as you can see here. And then when you plot these vectors in space, you discover similar words clustered together and relationships emerge that you can't see with the naked eye. So our research question becomes, if word2vec can learn that king relates to queen, can we teach a similar system that Apple can relate to Microsoft? And more importantly, do these stock embeddings reveal hidden structure in financial markets that we can't see? So why does this matter? AI can reveal hidden patterns in complex financial systems that traditional analysis misses. Understanding market structure benefits everyone, not just traders, but anyone with a retirement account or a pension fund. And then understanding, when we get a better model, we get more efficient markets and fairer pricing. As you can see in this visualization, AI analysis can take what looks like random and chaotic data and reveal clear, organized structure underneath. Academic insights like these translate directly to real-world applications that affect us all. So, research methods. How did we actually go about doing this? Well, we got 2 years of daily price data across 54 stocks. And those 54 stocks are divided between 6 sectors. What that means is that we have 15 for technology, 10 for finance, 10 for healthcare, 8 for consumer, 5 for energy, and 6 for industrial. We applied a word-to-vec style skip-gram training. That just means that we have one stock like Apple, and we're going to try to predict it from all the other 53 stocks. We're not going to show it, but we wanted to see if we can learn that model, right? And we're also going to teach the model that if Microsoft and Google are going up, Apple is probably going to go up too. But here's the key part. We didn't stop at static embeddings. Static models look at relationship as fixed. Apple always relates to Microsoft in the same way. Sequential models, like transformers, look at patterns over time. They learn that yesterday's Apple movement plus today's market condition predict tomorrow's better than anything looking at a fixed relationship. We compared these approaches to see what captured market dynamics better. So, systematic risk dominates was one of our major findings. We found out that all sectors correlate at about 0.74% regardless of the industry. Systematic risk is a market-wide risk that affects all stocks at once. Think about economic news, interest rates, or a global event pulling everything in the same direction. As you can see here, Apple correlates with JP Morgan just as strongly as it correlates with Microsoft. This means market forces, or systematic risks, dominate sector-specific patterns 95% of the times. This isn't a failure to find a sector pattern. It's proof that the model is correctly capturing how markets are working. But here's where it gets interesting. While systematic risk dominates most of the time, sector patterns do emerge, but they only happen during crisis periods. Here, as you can see in this chart, only about 5% of trading days show clear sector differences, meaning what's happening here where everything isn't moving exactly the same. And the answer to that is something is crashing on day 200. We're getting a dip. And during these stress periods, you can see technology and finance getting hit hardest, while healthcare and energy show more defensive behavior. So sector relationships do matter, but only when markets are under extreme stress, and that again is only at around 5% of the time. So this brings us to our performance results, and this is where the research really paid off. Static embeddings learned market structure correctly. but they missed timing patterns. They achieved a mean absolute error of around 1.544. Our enhanced transformer model performed better at 0.921. But surprisingly, the basic transformer architecture achieved the best results at 0.815 MAE. That's a 47% improvement over static embeddings. The key insight here is that sequential transformer models captured temporal relations that static approaches completely missed, and simpler architectures actually outperformed complex ones. So why did our basic transformer model actually outperform our other more complex models? This is because of the multi-head attention, which identifies which past days matter most for our current predictions. What that means is that sometimes yesterday matters more, but sometimes it was 3 days ago. The model learns this dynamically. Sequential patterns proved more important than static relationships, and our simple architecture avoided the overfitting problems that plagued the more complex models. So let's go ahead and summarize our key research contributions. We quantified the relationship between systematic and sector-specific risk in daily market movements. Systematic wins 95% of the times, but we revealed exactly when sector patterns emerge, and that's only during those crisis periods that only occur 5% of the time. We validated the attention mechanism work for financial predictions, achieving that 47% improvement, and we demonstrated that superiority of temporal modeling over static approaches for this domain. So in conclusion, this research shows that embeddings correctly learned market structure and systematic risks really does dominate most trading periods. Sequential modeling beats static approaches by nearly 50% when you account for temporal patterns. Crisis periods are when sector relationships actually matter for predictions. Simple architectures often outperform complex ones, and attention mechanism shows real promise for financial prediction tasks. The implications extend beyond just better models. They give us fundamental insights into how financial markets actually operate. Thank you, and thanks to Dr. Sam Ogden for being a great mentor and the faculty of Capstone for the guidance as well. If you have any questions, feel free to reach out, and I'll be happy to answer the best I can. Thank you.